Hello everyone, Dr. Chen here. So we're going to review condition in this lecture video. So for condition, we need to understand what's the difference between external force and internal force. It's very important because we're going to learn that if you have an isolated system, then the momentum is always conserved for the system. Now, what is an isolated system? Isolated system is an external force on the system is zero. Now you can have internal force. For example, you have object A, object B. Then the force between A and B, we call them internal force. Now the force from another object, which is not A and B, acting on either A or B or both, that we call external force. So if there is no external force, we call it isolated system. And from momentum, the definition of momentum, and then we learn impulse momentum theorem, right? If the external force is zero, then of course, the momentum of the system is conserved. So we call this conservation of momentum. One of the examples is that if you have two astronauts in space and the external acting on them is zero, and they can push each other and they will gain velocity. But if you add the momentum of astronaut A and astronaut B together after they push each other, it's going to be add up to zero. Or we should see the initial momentum. Now we can choose the initial moment to be center of mass and is zero. So this is conservation of momentum. Conservation of momentum. There is a condition. Now remember, if the vector sum of x force on a system is zero, the momentum is conserved. So we always need to understand what's the condition of the conservation equation. Now, I guess it will be helpful you just take a moment to recall what's the condition for mechanical energy conservation. And if you can just go back to the energy conservation lecture video and check whether what do you think is correct. Now remember, mechanical energy conservation is if the only force that's doing work is conservative force. The key is doing work. Okay. Now then we have condition. In physics, if we have condition, which means we already use the impulse approximation that the impulse by external force is negligible for this process. So basically, the force that it really dominates is from internal force from the condition. So we can safely make this statement. Whenever you have a condition in physics, we say momentum is conserved. And momentum is conserved for all conditions. To distinguish different kind of condition, that would be depends on how kinetic energy behave before and after the condition. We distinguish them, we group them into elastic condition where you have same kinetic energy before and after the condition. So there's no change of kinetic energy for elastic condition. So elastic condition give you kinetic energy conservation too. So we have Pi equals Pf, we have Ki equals Kf. Then this is elastic condition. And then we have a special case of inelastic condition. That if you have a condition and after the condition, those two objects stick together, they will have the same final velocity. And for complete inelastic condition is always inelastic. There's always kinetic energy loss during the condition. So now we have three, actually we should have two different kind of conditions. Elastic, there's kinetic energy is conserved, and the inelastic kinetic energy is not conserved. So we have energy loss during the condition. That's why we say kinetic energy after the condition is less than the kinetic energy before the condition. Now there is a special case of inelastic condition. If the object collide stack together, we call it a completely inelastic condition. For any condition, momentum is conserved. Only for elastic condition, kinetic energy is conserved. Only for elastic condition. So those are all the terminology we should be familiar with to solve condition problem in physics. So let's do an example. We have an 8 kilogram object moving 4 meters per second. Let's call this one ma. Call this one initial velocity of object A, positive x direction. And then I have a 2 kilogram object. Let me call it MB, moving 3 meters per second in the negative x direction. So let's call it VB1, initial velocity of object B. Now after the condition, the final velocity of MA is 2 meters per second in the positive x direction. So it's VA2. We want to find out what's the total kinetic energy of the system after the condition. So let's first sketch the situation. We have before the condition 8 kilogram moving 4 meters per second, and we call this one MA, VA1. And then you have 2 kilogram moving 3 meters per second, VB1. This is MB. This is before the condition. And then after the condition, what do we have? We have 8 kilogram moving 2 meters per second. Now we call it VA2, final velocity of object A. And well, the question didn't give us what's the velocity of object B after the condition. It asks us what is kinetic energy after the condition. K2, it should be calculated as 1/2 MA VA2 square, kinetic energy of object A after the condition, and then 1/2 MB VB2 square. This is KA2 KB2. It seems I already know what is MA, 8 kilogram, VA2, 2 meters per second. I know what is MB, 2 kilogram. I don't know this. So it's really about how to find the VB2. And it's a condition, right? is a condition. So apparently momentum should be conserved. I should have P1 equals P2. Can we solve the final velocity of object 2 using momentum conservation equation? So yeah, let's try. Let's try to write down the equation. Momentum conservation. So the condition tells us momentum is conserved. You have initial momentum equals final momentum. And the initial momentum and momentum of object A, momentum of object B before the condition equals momentum of object A after the condition, momentum of object B after the condition. Now plug in all the numbers. 8 times 4 plus 3 times the mass is 2. 2 times, okay. Now this time we need to go back and double check what's the velocity of MB. So we have choose this to be our positive x. So actually before the condition object the B is moving in the negative x direction. So the initial velocity of VB1 actually is -3. MA is 8. After the condition is 2 meters per second. And B is 2. So we have one equation, one unknown variable. We can just solve it. This is 32 subtract 6, 16 plus 2 VB2. 26, 16, so 10. So we can solve the final velocity of VB is 5 meters per second. Now we can go back here and calculate what's the kinetic energy, right? 1/2 8 times 2 square plus 1/2 2 times 5 square. And this gives us 16 plus 25 joules, 41 joules. This is our answer. So the final kinetic energy of the system is 41 joules. Okay, final equals 41 joules. Okay, now let's do a complete inelastic condition problem. It's very similar. Same initial condition. Now it's just after the condition, we don't know what's the velocity of either of them. It asks what's the total kinetic energy of the system after the condition. But anyway, it's a condition, right? And condition means momentum is conserved. So, and after the condition, MA and MB should stack together. So let me draw after the condition. After this condition, you have 8 kilogram, 2 kilogram. They should have the same velocity. Let's call it VF. They move together. And so we have momentum conservation equation. MA VA1 plus MB VB1, that's the initial momentum. Final momentum MA VA2 plus MB VB2, but VA2 VB2 they all equals VF. I can replace, let me keep it, MA VF plus MB VF. So it's MA plus MB VF. Now already calculated, the left hand side is 8 times 4, subtract 2 times 3, give me 26, right? So to solve this one, this is 10 times VF equals 26. VF is 2.6 meter per second. That's the final velocity of A and B stick together and move together. Okay, now I need to find the final kinetic energy of the system as before. Kinetic energy of object A, that's just the Ka2, Kb2, 1/2 Ma Va2, which is 2.6. 1/2 Mb Vb2 squared, which is 2.6 meters per second. So 1/2 Ma plus Mb Vf squared, 1/2 times 8 plus 2 times 2.6 squared joules. Now we need to use a calculator to find out the answer. 1/2 times 10, 2.6 times 2.6. Yeah. So roughly 29 joules. Okay. So hopefully we understand how to solve problem in condition now. I will see you next time.